Greetings, AP Chemistry. This is Mr. Harper, and what we're going to do here in this podcast is we're going to go through the solution, the complete solution to problem 42 in chapter 18, and this is going to be an example to you, hopefully, to help you in doing titration type problems, because I will tell you right now that you're going to have some on tomorrow's homework and also on the test, which is coming up on Thursday, the relentless exam. On acid basis Thursday, we'll have one free response question on titration, so you will need to know how to handle these types of problems. Also, towards the end of the podcast, guys, we're going to talk about indicator selection. You can also learn about that from reading your book, but if you'd like to listen to the lecture, then here it is. Okay, so let's go through. What it says in the problem is that you titrate 25 milliliters of 0.11 molar ammonia solution with 0.10 molar hydrochloric acid. And this is happening here in several parts, okay? And part A of the question is, what is the pH of the ammonia solution before the titration begins, okay? Before the titration begins, all we have is 0.11 molar ammonia solution. That's all we have there. We haven't added any acid yet. And so really what we have, guys, we have ammonia in water. Now, if I ask you guys, what kind of substance is ammonia, you're going to tell me, of course, that is a base, meaning that when you put that in water, it's going to accept a proton from the water. It's going to be transferred over there like that, and the products of this reaction are going to be ammonium ion and hydroxide. And so, if I want to know the pH of the solution, it's a simple process, just what we've been doing before. This is an ice table kind of problem, okay? My initial concentration of the ammonia, like it says in the problem, is 0.11 molar. As it reacts with water, the change here is going to be minus x. So at equilibrium, we have 0.11 minus x. And then here we're going to have plus x, and at x at equilibrium, and plus x, and then x at equilibrium. And so there we go. That's what's happening there in the solution. This is going to react to produce hydroxide ion. And so we have to make a prediction as the pH. The pH, guys, will be greater than 7. Next step is we're going to set up an expression for Kb. Kb here is going to be equal to x times x, which is x squared, divided by the concentration of the base at equilibrium, which is 0.11 minus x. I'm going to set that equal to the numerical value of Kb for ammonia, which is 1.8 times 10 to the minus fifth power. And of course, you're going to ask me, Mr. Harper, how do I know this is a Kb value and not a Ka value? That's, of course, because ammonia, guys, is a base. Okay, next question is, can we use approximation if we compare this Kb value is at least 3 powers of 10 smaller than my concentration of the base, so yes we can, that goes away, and now we solve for x. X here is going to be the concentration of hydroxide. If we solve for it, I'll let you guys do that at home. You should pause the problem and do that yourself, but the answer is 0.00141 molar. Therefore, to find the pH we can find by taking 14 minus the pOH of the solution, because this is the concentration of hydroxide ions, not hydronium, and then we find the pH is 11.15. And there we go. That part of the problem is relatively simple. Okay. Part B, going on. It says, what is the pH at the equivalence point? Okay, guys. What we're doing in this problem is we are taking ammonia and we are titrating it with HCl. This is going to react completely to produce ammonium ions and then, of course, chloride ions. Now, the chloride doesn't really matter. The important part here is the ammonium, because, guys, ammonium, what kind of substance is that? If I were to ask you that on the quiz or test, you should be able to tell me, well, of course, Mr. Harper, this is a weak acid, okay? At the equivalence point, what is special about the equivalence point is that we've added exactly enough HCl to totally consume the ammonia and completely change it into the ammonium ion. So, originally at the equivalence point, we're not going to have any of this stuff left, and we're only going to have the ammonium ion. Now, once the ammonium ion forms, right, this is going to go back and it's going to react with water. So you can kind of think about this as being kind of two steps. The first step is the ammonia reacts with the hydrochloric acid. These two things totally get converted into ammonium ion and chloride. Once the ammonium ion is formed, this will now go on to react with water and to produce hydronium ions, H3O+, and ammonia once again. Now, if I wanted to know what the concentration of my hydronium ion was once equilibrium has been reached, this is an ice table problem. ICE, okay? Where I have to make an ice table. Now, of course, you're going to tell me, well, Mr. Harper, we need to know a couple things first. First, I have to know Ka for my acid. Well, Ka for ammonium ion can be looked up, and it is something like 5.6 times 10 to the minus 10th power. But we also have to know the concentration of the ammonium ion that is there in solution. Now, to figure this out, we have to do a little bit of stoichiometry, okay? What I need to know in order to figure out the concentration of ammonium ion initially is I have to know the number of moles of ammonium that I have divided by the total volume of the solution in liters. Okay, well, if we go back and look, okay, we can find the Okay, guys, to find the concentration of the ammonia, we have to take the number of moles and divide it by the total volume of the solution, which is in liters. Well, the moles here we can get from the concentration of the ammonia, because we know that all the ammonia that we have at the beginning gets totally converted into ammonium ion. So we have 25 milliliters of that solution to begin with, okay? It has a concentration of 0.11 molar, so if we change this to liters, 0.025 liters times the concentration, 0.11 moles of ammonia per liter. Okay, we're going to get that we start with 0.00275 moles of NH3. Okay, now to find the total volume of the solution, well, we start with 25 milliliters of ammonia, but now we're adding hydrochloric acid to that solution to neutralize the ammonia. So I have to know the volume of my HCl that we add. So okay, let's go to a white screen here, guys. Okay, let's just figure out really quickly how much hydrochloric acid we have to add. Okay, so I start with my 0.025 liters of ammonia. Okay, I'm going to multiply here by the concentration, which is 0.11 moles per liter. Okay, so that tells me how many moles of ammonia that I've got. And now I'm going to multiply by a mole ratio, changes moles of ammonia into HCl. According to the equation, 1 mole of HCl reacts with 1 mole of ammonia. And now I'm going to multiply by the concentration of the acid, okay, where I'm going to put moles in the bottom. It's 0.10 moles of HCl in every liter of solution. So moles of HCl cancels, moles of ammonia cancels, and we're going to end up here with the volume. If we go through and we calculate, we get that this is going to take 0.0275 liters, or which would be the same thing as saying 27.5 milliliters. Okay, therefore, the total volume of the solutions is those two things added together, so we're going to get 0.0525 liters. That's my total volume. Okay, let's go back to the problem. Okay, if we find out the concentration from that, we got the number of moles. We're going to divide that by the total volume, 0.0525 liters, and we're going to get that the molarity of the ammonium ion here in the solution is, whatever it is, 0.0524 molar. Okay, now from here, because at the equivalence point we just have the ammonium ion in solution, that reacts with water and makes hydronium. Now it's just an ice table problem. The change in the concentration of ammonium is minus X, so at equilibrium we have 0.0524 molar minus X. Here we're going to have plus X, and here we're going to have a plus X, so at the end we have X and X. If we set up an expression for Ka for this acid, Ka is going to be equal to the concentration of hydronium times the concentration of ammonia, which is going to be X squared, divided by 0.0524 minus X. This is equal to the numerical value of Ka, which is 5.6 times 10 to the minus 10th power. Okay. Of course, we can't use the approximation here, so that simplifies a little bit. Pause the recording, guys. Go ahead and solve for X. Okay, we're back. You guys have found that X is going to be equal to 5.42 times 10 to the minus 6th molar. That is my concentration of hydronium ions. And so it's simple to find the pH from there. The pH of the solution at the equivalence point is going to be 5.27. Now, you may be tempted to say, well, wait a minute, Mr. Herbert, that doesn't make any sense. The pH here is acidic. Well, in the case when you guys are titrating a weak acid, if you titrate a weak acid with not a weak acid, but a weak base with a strong acid, okay, the weak base at the equivalence point gets totally converted into its conjugate acid. The ammonium ion is a weak acid, so if we have this in solution at the equivalence point, it makes sense that since we have an acid, the solution will be acidic. And that's always going to be the case, guys. When you titrate a weak base, you will always have an acidic solution at the equivalence point, and vice versa. When you titrate a weak acid, you will always have a basic solution at the equivalence point. Okay, that was part B. Part C, the question is, what is the midpoint, or what is the pH at the midpoint of the titration? Well, guys, we said that at the midpoint of the titration, you've halfway neutralized your acid or halfway neutralized your base. Now, we could go through here and we could set up an ice table, and I could show you guys how to find the pH that way. But the thing, probably the best way to do this is just to remember that at the midpoint of a titration, the pH of the solution, if you're titrating a weak acid or a weak base, is going to be equal to the pKa of the acid, okay, which you are titrating. In this case, my acid, this is the ammonium ion. This is the conjugate acid of ammonia. We could also say that at the midpoint of the titration, pOH is equal to pKb of the base, and then solve for pH from that. Either way you want to do it is totally fine. But this is a good piece of trivia you want to remember for when you go on Jeopardy later on in life. If you go through and just use that relation to find the pH of the solution, you're going to get that the pH at the midpoint of the titration is 9.25. Okay? Now again, sometimes people ask me, well, Mr. Harper, does that make sense? We have a basic pH here at the midpoint of the titration, and in this case, it does, because we are titrating a base. And so as we titrate it, as we add my acid, you can imagine that my pH is going to start high and it's going to start going lower, 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 but it's still going to be halfway before we reach the equivalence point, right? Because at the equivalence point, the pH shoots down, you know, something like that. Somewhere in this region here, guys, halfway through the equivalence point, we're still going to have a very basic pH, okay? So that does make sense. All right, that was part C. Part D.